Hey, what's up, guys? This is Chung here. So today, let's do something different. Let's try to implement a quad tree. And if this one video is too long, I will try to split it into two parts. Okay, so let's start. Here we go. So first thing first, so what is a quad tree and why it matters? So a quad tree is often used in a geospatial system like the Yelp or Uber's, because for those kind of systems, one of the important features is that, given like a range, given like a range, right? You need to find the points, or in Yelp, it's like the business. In Uber, it's like the drivers, right, around that area. So for example, given like this kind of a range, let's just assume it's a rectangle, right? We have a bunch of dots, right? Different dots in there, a lot of dots in there. And then there are like other dots on the outside here, right? Different dots here. And given like a range, you need to return all the points within that range. And how can you efficiently do it, right? The most the most naive way is that, we store each of the points. We store each point in the table, right? With the points information plus its longitude and the latitude, right? And then given a range here, right, we will have like a check method. And given a range here, we scan all the points in our database, and then for each point we check if that point's longitude and latitude is within the range. If it is, then we return. If not, we simply skip that. That's going to be a linear scan. It sounds like it's pretty okay, right? But assume that if this area is the entire Earth, right? And on Earth, how many business we have, right? We have like millions, or not even tens of millions business, right? And for Uber, same thing, right? So I think there are like in total, I don't know how many drivers moving at the same time. Probably, I would also say like at least hundreds of thousands drivers moving globe-wise, right? And to scan that like millions or tens of millions points at the same time, it's going to be very in performance, right? It's going to be slow. So that's why, we instead of, I mean, of course you can create some index, right? Of course, because if you do a select from where, right, where that select where the latitude and longitude is in the range, of course you can create some index on the table so that you can speed up the query a bit, but still it will not change the performance fundamentally. That's why we need to somehow find a better data structure to store those kind of points, so that we don't have to scan the entire domain, or you call it area, right? So, and the way the data structure we're using is called a quad tree. So why it's called a quad tree? So quad tree mean basically, quad means four, right? I mean, assuming we have this kind of area, and I'll just so I'm gonna erase those kind of stuff here. Actually, I'll just use this one. And assuming this is our entire domain here, okay? And we at the beginning, when we populate all the points, right? We just keep adding. We're adding the points into this domain until it reaches its limit. Basically, where it means a capacity or limit means that we're gonna set like a capacity to each of the rectangle. Yeah, I call it rectangles. Whenever the points inside this rectangle reach its limits, we'll split this rectangle into four parts, like this. let's say, for example, if the capacity is 4, so which means that we add 4 points to this rectangle first, right? We have 1, 2, 3, and 4. So when the fifth point comes in, instead of adding this point to this big rectangles, we're gonna split this big rectangle into 4 smaller rectangles, and then we'll find the correct sub rectangles, and then we'll add that point into that sub rectangle. So the reason to do that is that so that we can keep the points within the single rectangles at below this capacity, right? So that when we query each rectangle, it could be fast enough. Just like when we have a SQL table, we have a table in the SQL servers. When the tables when the table keeps growing, right? And then when the records in the table reaches like certain limits, like for example hundreds of 1 million or even 10 million records, query that single table will become very slow. That's why in the SQL world we have data partition, right? So we want to partition that big table into several smaller tables so that we can, and when we query certain records, right? And when we do the partition, you guys know we use a hash, we use hashing functionalities, right? And then based on the hashing range, we'll split the table into different subtables. And when we do the queries, we use the query key and we also hash that query key, and then we will look for the correct subtables we will look for, right? We need to look for. Same idea here. You know, whenever the whenever the points inside a rectangle it has reaching its limit, will split basically will split into 4 parts. And then of course, this 4 points will still be inside will still be inside of this big rectangle, right? But whenever the fifth comes in, it was stored in this sub rectangles. And then so let's say we have a second we have this one here, and then we have the sixth one here, 7, 8, right? Now so we have four we have 4 points into the sub rectangles here, and when the another one comes in here, right? What we're gonna do, we're gonna split this one into a 4 sub rectangles again, right? So we just keep doing it until we have basically there always could be a way we can divide, right, this big rectangle into 4 sub rectangles. And to better help us understand this rectangles better, I'm gonna name it to what? So this is north, right? North, south, west, and east. So I call this rectangle what? That's northeast, right? And this one is like what? It's southwest, right? This one is southeast. This is northeast. Oh, sorry. So which means that this one is northwest. Sorry. So which means every time when we split the rectangles into 4 rectangles, we'll basically we'll create 4 new rectangles within that rectangle. So why it's called a quad tree, right? And a root is the rectangle itself, right? And whenever we split this rectangle, we're gonna have 4 childs. It's gonna be northwest, northeast, southwest, and southeast, right? And when any of the subtree reaches his limit, which is the same one here, this one will also be split into 4, right? Same thing for this one, but we only split when it's necessary. If this one has not reached its limit, it will not have any subtree here. That's why it's called a quad tree. And as you guys can see here, with this kind of data structures, we don't have to query all the points. I mean, we can always start from the root, which is the central point, right? And given like a range here, we can always have like a helper functions inside of each of the rectangles. Given like a query range, we'll first check if the current rectangle has any intersects with the query range. If it doesn't, we simply ignore that. We completely ignore that branch. For example, if we have this big domains here, right? Then we have different. Let's say our query range is somewhere here. It's on the top left corner, right? And assuming we have 4 rectangles here, and then we start from here. And to start from here, we always query all the subtree, right? So first, if we are at this subtree here, and we check if this one has any intersection with the query range, there it's not, right? We simply ignore this part. Same thing this one, same for this one, and then we can only we'll only go for this part. And for this part, we'll keep going until we find a rectangle that has the intersection with our current range, right? As you got, then the time complexity will become to something similar like log n, right? And this log n will exponentially, right, decrease our time complexity. All right, so that's the brief description of the QuadTree. So whenever in the system design, I think the Yelp and Uber or Lyft, they're still using it, but I know there's another like way of doing this geospatial uh, a POI. It's called a POI search. One is the QuadTree, the other one is called S2. I think S2 it was introduced by Google. It's called the geospatial hashing, but we're not going to cover that technique here. So for this kind of videos, we're only focusing on implementing the QuadTree. Okay, so that's the brief introduction of the QuadTree. If you guys want to know more detail about QuadTrees, you can always Google it. There's a wiki page you can look for. All right, so let's try to start the implementation here. Okay. Mm, so first thing first, we need to create a few class here. Like I said, we need the first class we need is a point, right? So the point is like this, right? So by the way, I'm using Python because I've been using Python for a while, so that's why I'm using the Python syntax here. So for all the other language, the concept should be similar. Okay, so for a point, it's pretty straightforward. All we need is just two properties, the x and y, right? So which means that in the point we only have two properties. X is x and self.y is y. So that's it, the point, right? And the second class we have is like what is the rectangle, right? So the rectangle is like the range of sorry, it is a range, right? So a rectangle, how can we uniquely identify a rectangle on the 2D grid here? So one of the ways I'm using is like this, we have, oh, and by the way, so I'm starting from this. So I'm starting from this one. This is 0 and 0. So with the rectangles, if we know the center point, and then if we know the this is the width and this is the height, and this is the center point, right? If we know these three properties, then we can uniquely identify a rectangles, right? So that's exactly what we're going to use here. So first thing first, we need a center point. So keep in mind the center here is a point class. It's like this one. So this center has like x and y. I'm just using a point object for it. And then we have the width and the height. So keep in mind this width and height is the half width of, it's like the half width of the entire rectangle. Same thing for the height here. Okay. So that's that. And also to do that, let's just populate the centers here, right? We populate the center point here, and then we populate the width, right? The width, and then width self dot height equals to height. Okay, and after this one, I'm also going to introduce 4 more properties. It's called west, east, north, and south. So why do I need that? Basically, I need the coordinates of this left edge, this this left one, the top one, the right one, and the bottom one. We need this. I need those 4 edges because I need those 4 edges to help me calculate some logic later on. That's why I'm going to define it here whenever we have a rectangle, so that later on I don't have to recalculate again. So what is the west? So west is center dot x minus width, right? So we have a center point, and what's the axis? What's going to be the edge on the west edge here? So it's going to be the center minus the width, right? Same thing for the east is going to be center x dot plus the width, right? And then I have this center dot y minus the height, right? And then same thing for the south edge, center dot y plus height. So the reason I do a minus and the plus here, remember, so I'm using this axis, x and y axis. So the top left corner is a 0, and then here is the x is always increasing, and the going down means the y is increasing. That's why the south means plus and the north means minus. Okay. All right, so that's that. That's the rectangle, right? And then we'll add more functions later on. But so the next one is the real QuadTree class. Okay. So for a QuadTree, actually, the QuadTree is it's actually a rectangle, but the only difference is that a QuadTree is a rectangle plus a capacity. That's why when I initialize a QuadTree, right, I have this thing here. So we have a self, right, and then we have a boundaries, right? Because for QuadTree, I use this boundary is a rectangle. I use the rectangles to help us identify the boundaries of this QuadTree, right? And then the second one is a capacity. So at the beginning, by default, I will give it a 4, just to help us to do some testing. Okay, and then same thing here, we have a boundaries, right? Boundaries equals to the boundaries. And then we have a self dot capacity, right? Equals to capacity. And then the next one is what? The next thing is that a point, right? We need a list to store the points within this QuadTree. That's why I'm simply using like a list to store all the points for this QuadTree. And the last one is actually it's a Boolean flag to tell us if this QuadTree has been divided or not. So at the beginning, it is false, right? Okay, cool. So so that's the 3 basic class we're gonna be using. We're gonna be using later on. So now the first thing first is that we have these 3 kind of class here, and now the first function we need to implement is the insert, right? Which means we're inserting a point into this QuadTree. That's why I'm going to implement the insert function first. So the insert function will simply take like one parameter, which is the point. It means that we're inserting a point into this current QuadTree. So to insert it into the current point, the current QuadTree. So first thing first, what we need to check here. So first we need to check if the point is in the range of current quad tree, right? Because if it's not in the current quad tree, we'll simply return it. So that's why, if not self dot boundaries, right? That's why we have a boundaries. Oh, that's why we in the boundary in the rectangles here, we're gonna have like helper functions to help us check. Given like rectangles and a point, it will tell us if that point is within this rectangle or not. So assuming we have a function called contains point, right? And then we pass in this point here. If it's not contained, we simply return false. Will not continue. Then let's try to implement this contains points helper functions here. So here we have a defined contains point. Okay, self dot point. So this thing is pretty easy. We simply return, right? We simply return the self dot west. The point x is within the range of self is within the range of left and right and the west and the east and right. So that's that and right and what and the self dot north, right, is equals smaller than the point of y, smaller than the self dot south, right? We can simply return this one because this will give us will tell us if this point is within this rectangle. But one more thing we need to be careful here is that how about the points on the edge itself, right? For example, if the point is on the edge on either edge, which rectangles we're going to which rectangle will contain that. So a simple way to do it, we just need to put one of the two. We just need to put two edges, include two edges. Basically, we're saying that if the point is on the west edge and on the north edge, then we are thinking it's within this kind of within the current rectangle. If it's on the other two sides, then it should be on on the other rectangle, so that we won't have like a double counting, right? All right, cool. So that's that, to contains the point. All right, come back to this quad tree here. So if this one is not in the boundaries, we simply return. If it is, then we do another check. So what do we need to check? We need to check if the current quad tree has reached its limit. Okay, which means that so first it means that if the length of the self dot point, right? If the point is smaller than the self of the capacity, right? If it's not has not reached the limit, we simply do a self dot point and then dot append this point to the list, and then we return like a true or false because we will need this true or false later on to help us identify if this point has been inserted to any of the subtree. Okay. All right. So that's that. And all right. So now the next one is the if has not reached capacity, right? Then we insert. So now we have reached the capacity of this current tree. So the next thing is that we need to split that, But there's like also a second check here, or actually a third check, because if this current tree, the quad tree has been already been split, then we cannot split it again, right? So which means that if not self dot divided, right? Then we do a self divide, right? Yeah, so that's I'll just finish this insert function here, and then we'll implement this divide first, because inside the divide here, we'll after the divide here, we'll set this divided with into true here, right? And then after this, assuming we have divided this quadtree into 4 subtrees, then we will try to insert this. We'll try to insert this point to all those to any of those 4 subtrees, right? Basically, we're calling a recursive. We're making a recursive function call, right? Dot insert, and then we have a point, right? So if this, remember, so this north south dot northwest, it's also like a quad tree here. And this quad tree also has like an insert function. That's why this is like a recursive call, right? And this one, if this one is true, we simply return true, right? And then else if south dot northeast dot insert, right? Then point, then we return true as well. So I'll just make a copy to all 4 subtrees here: northwest, northeast, southwest, and southeast. Okay, and then in the end, we simply return false. Actually, you know what? Actually, we should never reach this return case here, because whenever we reach the another subtree here, if it's already full, it will try to divide again, right? So it should always find a place to insert that point. All right, so now let's try to divide this quad tree, right? So we have an insert and then we have a divide here. Cool. So let's define like a divide. So the divide is we don't need anything, right? We just so for divide, okay. So for divide, we have a rectangles, right? And this is the center point, right? And this is the width, this is the height. If we try to divide this one rectangle into 4, we need to find those 4 centers first, right? This is the center 1, 2, 3, and 4. As long as we can find those 4 centers, and all is left, we just need to pass in the half of the current width and half of the current height, and that will give us the definition of those 4 new rectangles, right? All right, so that's why we need a center x equals the self dot boundaries dot center dot x, right? And then we have center y here equals the center self dot boundary dot center dot y. And then I'm going to have a new width here. New width is equal to the self dot boundaries dot width divided by 2. Height equals to self dot boundaries dot height divided by 2. So now the first one is the northwest one. So for each of the sub quadrants, we need to initialize the rectangles first. So the rectangles, right? So for the northwest, which is this one, right? So for the northwest, in order to find this one, we need to do this, right? We need to use the center point. So the center point is like this. Center point is the current center, right? Minus new width, right? That's how we get the x value for this center. And the y value is also similar, like center of y minus the new height, right? Because remember, so I'm doing this kind of 0, 0 here, so this is a 0, 0. And we're increasing x to the right, and we're also increasing the y down going down. That's why for this one we have to subtract both the new width and the new height. Okay, so that's that, and then we have a new width and a new height. Okay, so that's the northwest rectangles, and then with that we can simply do the northwest, right? South equals to the new quad tree, and we just pass in this new west, the northwest. I mean, since we when we create the constructor for this class, we default it to 4, so which means that we can skip that, you know. That's why I don't have to pass in a 4 here. If you want to give it a different capacity, you can pass in here. Otherwise, you can just keep it here. You can skip that. So I'm going to copy and paste this 4 here. No. So now the next one is the northeast, right? So for the northeast, we have this. This is the northeast. So for northeast, we have this one plus, and this one stays at minus. Okay, so now it's northeast, northeast, right? And then the third one is the southwest. So for the southwest, I update this one first. For southwest, we have this one and southwest. So this one is the plus. The Y is plus, and the last one is the southeast, right? Southeast, and then the so for this one, they're both plus. Cool. Yeah, and then in the end, let's see. Actually, let's move this one inside of the divided so that it could be fully encapsulated, so that we don't have spread out this logic into 2 places. We simply do this, you know. Right. So, oops. True. Right. That's that. Divided. Okay, it's divided. Yeah. Divided. All right. All right, cool. I think, you know, that's pretty much it is, you know. That's how we recursively add a point to a quad tree. I think that's pretty much everything. And south, I think I made south, th. So now let's do something fun. Let's try to visualize this. Let's try to visualize this like kind of quad tree, you know. So to visualize a quad tree, we have to use some of the helper, some libraries, you know. The I think first things we need to use. So let's use a numpy here, you know, as numpy, you know. So for this part, you guys can just skip that, you know. It's just like a visualizations, you know. To visualize it, we have to create like a draw functions inside of these rectangles, right? Basically, you know, we have a define like a draw here, you know. So here we have some, you know, you guys can just skip this part. I'm just simply typing the code here, you know, the line width, the line weight is 1, you know, and we have this kind of args, you know, here do I have x1 and y1 equals to the south dot west, right? And then we have south dot north. That's the the top left corner point, and then we have a x2 and y2 equals to south dot east, south dot south, right? And then we just use this ax dot plot x1, x2, x2, x1, x1. So y1, y1, y2, y2, y1. And then we have a c equals to c, and the line weight equals the line weight, and then we have these parameters here. You know, this is just a template. You guys can totally ignore this part. You know, I'm just simply implementing a draw function for each of the rectangles so that we can draw rectangles on the board. You know. Okay, so that's that. You know, let's see if there's anything I miss here. And oh yeah, let's try to implement another helper functions for the quad tree. So because we want to know how many points within this quad tree. Remember, the length of the points is only can only tell us the capacity, but it will not tell us the what's the total points, including all the subtrees. So to do that, let's try to let's override the length function, right? Let's override the length functions to help us get the values. So first we have the current points, right? So the current count is what is the length of the self points, right? And then if self dot divided, right? And then count, okay. So the count will be equal to the length of the self dot northwest plus. And as you guys can see, here is also like a recursive call because for each of the sub quadtree, we'll also call it its own length function, which will be going in here, right? That's how we recursively calculate all the points: northeast, northwest, northeast, southwest, and southeast. Yeah. Okay. Cool. So here we simply return the count. All right. And quad tree. Oh yeah. So and since this is to only draw like the rectangles, but to recursively draw all the quad trees, we also need to implement another draw functions, inside here, right? That's gonna be the draw color, right? For the quad tree, But here we simply do a self dot boundaries dot draw, right? We draw this, we're passing this construct object, and if the self dot divided, right? And here we have another recursive call, right? Northwest dot draw, right? And AX here, okay, northwest, northeast, and southeast, and southwest. Okay, this is how we recursively draw the rectangles for all the subtrees. Okay, so I think with those kind of functions created, we can try to implement our test class here. So for the test class, I'm going to import a few things here, numpy as numpy, right? And then to draw the diagram, we have to use a matplot library, right? And .py lt as plot, okay? And then we also need to import all of our classes, right? Of course, we have from QuadTree, we have point, we have rectangles, and then we have a QuadTree, right? And then the third one is like this. We also need this one from import this one. Okay. All right. So let's define some helper functions here. So let's define our range first. So the total domain here, we have the width and the height. I'm going to define it as 600, and then the 400. That's gonna be our total length, right? The total area for our testing. And then let's try to generate 500 random points here, right? So I'm just using the random function. NumPy, there's a random function here, dot rand n, right? So we generate 500 random values, right, from zero to 1, and then I'm going to multiply by the width. So that's that, and then we have a ys. So the y is like the same thing here, right? But the only difference that we're gonna to multiply by the height. So now we have a 500 points equals to this, right? The point, the x as I, then xy, x as, oh sorry, y as I for I in range n, right? So now we have 500 points here. All we need to do is we just need to we just create a domain here. So like domain is a rectangle, right? The big rectangle. The point is, so the center point. Center point is like what? It's the half of the width and the half of the height, right? And then the width is also the half of the width and half of the height. So that's that. And then we have a quad tree. Let's do this quad tree here, right? So in the quad tree, we're passing in this domain here, right? And then we can, let's just use 4 as a default. So now we have a point, right? Let's try to use a for loop to insert each of the points here. We just simply do a QTree dot insert, right? We do a point. Okay, cool. So we have that, we can do some print here. We can print like total points, right? And then we total points inserted. We just do the length of the quad tree. That can give us the total points we have inside this quad tree. So now let's just draw put those points into this 2D grid here. So I'm going to use some like plot dot figure, right? Fig size to I'm just find this code from the from somewhere DPI, the 500, DPI dot is DPI because DPI, and then we have this AX equals to a plot dot subplot, right? The AX dot set xlim width and AX dot set ylim height. Okay, and then Q. In the end, we simply draw, right? We draw we draw those rectangles. Here we're drawing the rectangles. Now let's try to draw the point, right? The point is like this: AX dot scatter. P dot X. I'll just copy and paste this one here. So this is how we draw draw the points. We draw the point here. Draw rectangles. Draw the points. And then in the end, we just okay. I need to invert these things here for the y-axis because the way we're defining that it's a little bit different And then I'll just do this thing here. Okay. All right. That's it. Okay. So let's try to test. So let's try to test these things here. Okay. Let's try to run this code here. Oh, we have some arrows here, I think. Yeah, this one here. Okay, let's try it one more time. Start debugging. Okay, cool. So as you guys can see here, right? I mean, that's how the this QuadTree have been generated. We have a bunch of we have 500 random points within these 2D grids, and whenever there's more than 4 points in an array, it will be subdivided into four different QuadTree. For those kind of, we have five here. Why they didn't get subdivided? Because I think this is because of the way this visualization code works. But just ignore that. So as you guys can see, so for this part, right, we have a 1, 2, 3, 4, 5, 6. Now when more points are coming in, there have been further subdivided into four different trees. Okay. So that's like the 500, right? We can try. How can I remove that? Okay, let's try. We can try 1,000. Let's see what happened if we do a 1,000 points here. All right. So now we have doubled the points. So as you guys can see, have been more QuadTree have been created. Okay. Yeah, and that's how we use QuadTree to store all the points. And yeah, I think for this videos, I would stop here because it's already long enough. And in our next videos, we're gonna implement the query part, basically with given like this kind of QuadTree, right? Given like this kind of a QuadTree, and also given like a range, how can we find the points within that range? For example, if this is the range, and how can we find that? And we'll be using the QuadTree to help us find that. Okay, sure, cool. And I think I'll stop here. Thank you so much for you guys to watch this video. Stay tuned and wait for the part two. Bye bye.